Let's review real quickly the definite integral, our definition for the definite integral. And so this is what we derived in the last section and the last video. We went through this again. So the definite integral comes from looking for the area, the net area between a function and the x-axis on an interval from a to b. And so we do that by looking at rectangles, and that gives us this definition for the definite integral. The integral from a to b of f of x is the limit as n goes to infinity of f of x sub I star, where f of x sub I star is a tag. We do tend to pick our tags to be the right-hand endpoints most of the time, but we could do left-hand endpoints, midpoints. We can do all points within a subinterval. It doesn't matter. If this limit exists, we say that the function is integrable, and we can calculate that limit using some sum rules. So we started to explore that. We're going to do a couple more examples on this video and get a little bit more into this idea of net area between the function and the x-axis. So we're gonna talk a little bit more about that. And so just as a reminder, I'm projecting this up again on the screen here so that we can see what happens if we use the right-hand endpoints. We get that tag to be just x sub I, and if we use the left-hand endpoints, the tag becomes x sub I minus 1, and if we use the midpoints, then it's x sub I bar, where we are finding that midpoint between x sub I and x sub I minus 1. Now, real quickly on this, we remember also for all of these that delta x, it's off the screen, it was at the top, b minus a over n. And we can use that along with our starting point A to figure out what those endpoints should be. So let's go ahead and get into an example. I actually have the graph of it right here, pulled this out of Desmos, and let's take a function f of x equals x cubed minus 3x, and let's set up the expression to represent that area and get the summation in terms of just I. Then we'll actually evaluate the limit using our sum rules. I want to focus on B, actually. I want to look at this from 1 to, actually I want to do 1 to 2 because that's what I have on the screen. So let's go from, rather than 1 to 4, let's go 1 to 2. So let's focus on this example, but let's go from 1 to 2. And the reason I want to go from 1 to 2 is because, as you can see, this is actually the curve of the function. Y equals f, let's say y equals, this is y equals f of x, but I'm going to write f of x in, x cubed minus 3x. What you can see right here, and I'm going to do it in 2 different colors. Let's go ahead and do, underneath the x-axis, notice that the area here, this is 1, notice that there is area both under the x-axis and area above the x-axis. And the integral is giving us the net area because as we actually build rectangles, and that's what our limit is doing, as we build rectangles down here, these rectangles are going to actually have negative heights. So these rectangles are going to have negative heights, and then the rectangles above the x-axis on this portion from this the 0 right here to 2, these rectangles are going to have positive heights. And so when we add all those up, we actually get, when we take the integral from 1 to 2, which does represent, when we write that integral from 1 to 2 of x cubed minus 3x dx, what that represents is the net area of the curve y equals x cubed minus 3x. Okay, so that's giving us the net area, this idea of net area. Basically where we take the negative, and we haven't ever really thought about area as negative, but we think of the area that is under the x-axis as the negative area, and the area that is above the x-axis as the positive area. When you add that negative and positive area together, you get the net area. Okay, and we would get the net area. So our integrals can be positive or negative. They still represent an area, it's just a net area. Okay, so let's go ahead and do that. Made that quick switch from 1 to 4, but let's look at it from 1 to 2. So let's take, and we've already written it as its integral. I'm going to rewrite the integral down here. So let's take the integral from 1 to 2 of x cubed minus 3x dx, and let's write that as a Riemann sum. So that is going to be the limit as n goes to infinity of the sum of all of the rectangles from 1 to n and heights of rectangles x sub I star times delta x. So using my definition, but also intuitively just remembering that that integral comes from the idea of looking at areas, and the way we look at areas is we compute areas, we add up the areas of n rectangles. And these are our rectangles because this is the height of our rectangles times the width of our rectangles. Okay, we're going to go ahead. Actually, I don't know. Did we say right hand? I did not say right hand endpoints on the instructions here, but let's go ahead and use the right hand endpoints. The right hand endpoints tend to be the simplest endpoints to use, and let me explain why one more time. Because if we're going to divide up the interval from 1 to 2, okay, so here is my A and here is my B. I'm going to divide it up into widths of delta x. Now delta x is going to be 2 minus 1 over n because it's b minus a over n. So delta x is going to be 1 over n. So we're going to divide this up into n intervals. Here's x sub I minus 1, x sub I. Here's the ith interval, the generic ith interval. We're going to go ahead and use the right-hand endpoints, x sub I. And we just need to figure out how would I express those. So the tag that we're going to pick, x sub I star, is actually going to be the right. Sometimes we're told what we have to pick, but I want to pick the right-hand endpoints. And in doing so, I can just write x sub I, because the right-hand endpoints of an interval, each subinterval is x sub I minus 1, x sub I. And so I drew that on the picture, but obviously the right-hand endpoint of a subinterval is the end of it, okay? The endpoint of the interval. So we're going to pick our endpoints to be x sub I, and what we can do is we can think about, well, how could I express that based on where I started at and what delta x is? Well, remember that delta x we just showed was 1 over n. So 1 over n, each of these widths is 1 over n. So this first one, remember this time we didn't start at 0, we started at 1. So x1 is going to be 1 plus 1 over n. And I don't have a ton of space right here. I think I'm going to write those vertically actually. So x1 is 1 plus 1 over n. And then of course x2 is going to be 1 plus, now we've gone 2 widths, so 2 over n. So by the time we get to x sub I has to be equal to where we started at, a, plus we have I of those delta x's, which were 1 over n. And so notice this is a nice little result for the right-hand endpoints. Our right-hand endpoints, when we look at right-hand endpoints on an interval, the right-hand endpoints of subintervals of an interval from A to B, our right-hand endpoints end up giving us this, we do get this formula. So if we know delta x and we know A, we can find what the right-hand endpoints are. So kind of a nice little note, make a little note in your notes that this is handy. Right hand, if you're working with right-hand endpoints, this is a handy expression. Okay, so we know what our right-hand endpoints are, we know what our delta x is. Let's get back to the integral and let's actually plug that in. So the integral from 1 to 2, which again, remember what that represents, that net area, that is equal to the limit as n goes to infinity of the sum from I equals 1 to n. Now our f of x is x cubed, but remember we're actually plugging in f of 1 plus, and I'm going to write this as I over n, okay, because that's the right-hand endpoint, so we're going to plug that right in, times our delta x, and delta x is 1 over n. Okay. Now let's go ahead and plug that in. We're going to ultimately evaluate that sum and take the limit, but before we can do that, we got to plug that expression in. 1 plus I over n cubed minus 3 times 1 plus I over n times 1 over n. Okay. Now let's go ahead and let's finish out that expression. I'm going to go ahead and cube that, distribute the 1 over n, and get this nice and cleaned up so that I can use my sum rules to actually evaluate this sum. So using just my rules for cubing a binomial, I'm going to get 1 plus 3 times I over n plus 3 times I squared over n squared plus I cubed over n cubed minus 3I over n. And then I'm going to go ahead and distribute the 1 over n. Three I over n squared plus 3I squared. Oh, you know what? Let's go ahead and let's go ahead and combine like terms before we do that. I just caught that. So this is actually, I'll do that in a different color, minus 2 and then distribute the 1 over n. Okay. All right, so working our way through this, and then I am actually going to apply some of my sum rules, and I have those sum rules down here. So let's go ahead and actually I had them off to the side. I know I have them somewhere. Here they are. So let's go ahead and use our sum rules because I see that we have an I squared and an I cubed. So we are going to use, we also have a constant. So we've got the constant minus 2 over n, and we also have the I squared and the I cubed. So we're going to go ahead and use our constant rule, sum rule from here, and our I squared and our I cubed rule. So here's our I squared rule, and here's our I cubed rule. So we can use those rules. Technically, I guess we're using almost all of these because we're actually using the sum and the difference rule as well, because we're going to break this up into multiple sums and then apply where I see the I squared. When I sum I squared from I equals 1 to n, I get this expression, n times n plus 1 times 2n plus 1 over 6, and I cubed becomes n times n plus 1 over 2 quantity squared. So I can apply those rules, and where I have a constant, when we sum up a constant n times, we get c times n. And it turns out that minus 2 over n is a constant. So we're going to go ahead and use those rules. We're going to plug those in, and then we'll be able to take the limit. So we're going to actually do the summation, and then we'll be able to do the limit. So the constant minus 2 over n, and minus 2 over the n, by the way, is a constant because we are indexed in terms of I. N is a constant, so it's a fixed constant. The limit, we're going to take the limit as n changes, but it is a fixed constant in the summation. So this is going to be minus 2 over n times n, because that's a constant, plus 3n cubed times, and the formula for I squared. So when we do the formula for I squared, we get n times n plus 1 times n plus 2 all over 6. I'm sorry, that is actually 2n plus 1. And then the formula for I cubed. The 1 over n to the fourth is a constant, so 1 over n to the fourth in terms of the sum. And n cubed, the formula is n times n plus 1 all over 2, and it is that whole quantity squared. Okay, so now we do have a bit of algebra to do here before we can take the limit. So let's go ahead, clean up the algebra a little bit and simplify, and then we can actually run the limit through. So here we actually have our final answer. Took a little bit of time. I sped that up so that you could just kind of watch that process of expanding those sums once we had replaced those sums with their expressions in terms of n, simplifying, expanding, and then taking the limit. And each of the terms, of course, that had a constant divided by n to some power in the denominator went to 0. And then just the final result ended up being -3/4. And, we can kind of get lost in what we're doing, but remembering that this is representative of a net area. And so if we go back to the graph that we had up here in the beginning, and I'll get rid of my rectangle. When we look back at this again, and let's get rid of the rectangles that we'd had there before, if we think about how much area is actually underneath the x-axis, and I will do that in a blue, you can see that there's more area underneath the x-axis, which would generate the negative, versus the area above the x-axis. And here I'll sketch that in there. And so we're getting the balance of those. If you want to think about it, you could think of this as, call that B, and this A. And when we take this integral, we're actually getting A plus B here, but A is bigger in size, but it's negative. And so when we take those and we add them, we get a net area that is negative. The balance, there is more area under the x-axis than there is above the x-axis in this case. And I didn't get that A labeled there. Okay, and so that's where we're getting that negative, and that does give us that does give us something to think about when we think about what we're doing when we're taking a definite integral, when we're looking at those areas. So again, went through that process one more time, finding an expression using the definition, using right-hand endpoints, plugging those in, and then applying all of my sum rules to come up with that. So let's just wrap this up with just one more example where we don't go through the whole process. In fact, it's not possible for us to go through this whole process because we don't have sum rules for every type of function, but we can do it for. So let's just to end the video, let's do one more of these where we write, and I'm going to go ahead and just pick this guy. Let's write the integral from 0 to pi of the sine of 5x dx as the limit of a sum. Okay, so let's use our definition of the definite integral. And now we have to just figure out what would be our delta x and what would be our tag so that we can plug those in. Now I'm going to go ahead and do the same thing. I'm going to say let's use our right-hand endpoints because those are the easy ones to pick, right? And in an interval from x sub I minus 1 to x sub I, a subinterval, the right-hand endpoint is that x sub I. So let's go ahead and use x sub I. Our delta x, now our a and our b, right, this time we're actually just given the integral. We're not even asked it in context. So our a and our b are 0 and pi. So our delta x is going to be pi minus 0 over n, or just pi over n. So delta x is pi over n. And then x sub I, one more time, let's do the visual. X sub I, here's 0 and here's pi. And as we go along, each of our intervals is pi over n. So each of these is a pi over n. Each width of these is pi over n. So by the time I get here to my x sub I will have added up I of those. And so we started at 0. So x sub I is going to be 0, the a value, plus I of those delta x's. So I times pi over n. So x sub I, my tag, is going to have to just be pi times I over n. And that is my tag and my delta x. And so I can finish out expressing this integral as a limit of sums. by plugging those in. So this is the sum from n equals, actually let's come down below so I have a little bit more space. So this integral from 0 to pi of the sine of 5x dx is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of, remember our x sub I, we're going to actually plug that in now. So that's going to be pi I over n times our delta x, and our delta x is pi over n. And so this is going to be the limit as n goes to infinity of the sum from I equals 1 to n of the sine of 5 pi I over n, because I'm plugging in my x sub I, my tag, times pi over n. Now, we do not have a sum rule for the sine of 5 pi I over n. And so this is as far as we're going to get in this section. In our next section, we actually will have a way to determine what this integral is. But in this section, right now, this is as far as we're going to get. This is the limit. This does express it. This is a Riemann sum. Okay, we've created the Riemann sum that expresses the integral. And we can leave it like this for now, knowing that this would represent the net area under the curve y equals sine of 5x from 0 to pi.